We've talked some about the properties of the sampling distribution of the sample proportion and the sampling distribution of the sample mean, and we've taken a look at some applets to better understand those concepts. Now we're going to do a couple of examples applying what we've learned. So example 3, it says, according to Lynn, EDU, 55% of American college students travel to an exciting destination for spring break. For this problem, suppose that the true proportion of American college students who travel to an exciting place for spring break is 0.55. We're going to consider a random sample of size n equals 60 American college students. We want to know the mean and standard error of the sampling distribution of the sample proportion of students who travel to an exciting place for spring break. Okay, so let's go ahead and write down some key information. We're told that we can assume the population proportion is 0.55, and we're thinking about a sample of size 60. Okay, and so we've learned before that the mean of a sampling distribution, so the mean of the sample proportions for a sampling distribution, where n equals 60, or any other number for that matter, is just the population proportion. So 0.55. All right. Now, the standard error of the sampling distribution of the sample proportion is the square root of p times 1 minus p over n. So in this case, that's going to be 0.55 times 1 minus 0.55 divided by the sample size 60. All right, and so this is 0.0642. All right, so let's just remind ourselves that this is a sampling distribution of a sample proportion. We're dealing with a categorical variable. That is whether or not the student goes to an exciting place over spring break. Note that we are given the population parameter, that the population proportion is 0.55. It's a little bit unrealistic, but remember in this chapter, we're starting by knowing the population parameters, and then we're studying how samples from that population behave. Okay? And so we said that the mean of sampling distributions is centered at the population proportion itself, and so that's why P equals mu sub p hat, which is 0.55. And then we're saying the proportion in the actual sample is going to vary, and a measure of that variation is 0.0642. That's the standard error of the sample proportion. So in other words, when we take one sample of 60 students, the proportion who've traveled to an exciting place will be different, most likely, than our next sample of 60 students. It's going to vary from one set of 60 students to another. Okay, so is it safe to assume that the distribution of sample proportions is bell-shaped? So when we have a categorical variable, our check for that is n times p at least 15, and also we need n times 1 minus p to be at least 15. So we're just going to check to see if that works out here. So I've got 60 times 0.55 for n times p, and I'm going to have 60 times 1 minus 0.55, which is 0.45, for n times 1 minus p. And so let's see what that works out to be. Okay, so this is 33, and this is 27. Those are both at least 15, so that checks out. So I'm going to say, yes, it is bell-shaped. And for the sampling distribution of the sample proportion, our rule of thumb is that if n times p and n times 1 minus p are both at least 15, then we have a bell-shaped distribution for the distribution of sample proportions. So part C says, in one random sample of 60 American college students, only 25 had traveled to an exciting place. Calculate the z-score for this observation. And we have a hint to find the sample proportion first. So let's go ahead and figure out that p hat, or this one sample that we've observed, has a sample proportion of 0.417. Okay. .417. And now I want to say, what is the z-score for this? So recall that a z-score is x minus mu so x minus mu divided by sigma. Now, in this case, our observed x is actually a sample proportion. So I'm going to rewrite this a little bit. We're going to take p hat and subtract the mean of the p hats and divide by the standard error of the p hats. So the observation we're actually interested in here is actually a sample proportion. So we're going to subtract the mean of the sample proportions divided by the standard error of the sample proportions. And we already found those values in parts A and B, so that makes life kind of easy. So 0.417 minus 0.55 divided by the standard error, 0.0642. Okay, and so that result is negative 2.07. A common mistake that I see that students make when I ask this kind of problem is that instead of using the sample proportion, they use the count 25 to do this calculation, and that's going to give you a result that doesn't make much sense. All right, and in fact, I want to go ahead and draw for you, I'm going to skip past example 4 right now, and I'm just going to grab some empty space. I want to show for you the relationship between some of the findings that we had for the binomial random variable and the sampling distribution of the sample proportion. When we looked at the binomial distribution, we focused on the count of successes. When we looked at the sampling distribution of the sample proportion, we focused on the proportion of successes. So let's make a table now, and let's look at the mean and the standard deviation for both the binomial random variable and the sampling distribution of the sample proportion. And hopefully you can see the relationship between the two. Okay, so I've started a table here. And again, when we talk about the binomial random variable x, we are focusing on the count of successes, which we call x. And with the sampling distribution of the sample proportion, we're focusing on p hat. Now notice that p hat is just the count of successes divided by n, so x over n. Notice also that the mean of the binomial random variable is just n times p. All right? And the mean for the sampling distribution of the sample proportion is just n, is actually just p. But I'm going to actually write it like this: n times p over n. And then, of course, the n's cancel out, and we're left with just p. All right, and now let's finally take a look at the standard error. Sigma for the binomial random variable is the square root of n times p times q. All right. Now, I could also write this like this: n times p times 1 minus p. The standard error for the sampling distribution of the sample proportion, if you take n times p, if you take the formula that we started with for the standard error, n times p times 1 minus p, and you divide it by n, you get the square root of n times, or I'm sorry, p times 1 minus p over n, the square root of all that. All right, so my point in showing you all this is just to help you see the connection that if you take any of the formulas for the count of successes and you divide it by n, then you end up with the same result for the sampling distribution of the sample proportion. So basically all the formulas for the count of successes equal the formulas for the sampling distribution of sample p if you divide them by n. All right, so I just wanted you to make that connection. All right, let's move on now to example 4. In example 4, we're looking at the average student loan debt for 2016 college graduates. It was about $37,000. So let's suppose for this problem that that is indeed the population mean student loan debt. And let's also assume that the population standard deviation is $10,000. All right, so I'm going to write this down. We're going to write this key information down. So I'm going to write mu equals 37,000. Sigma, that's the population standard deviation, is $10,000. So it says Kevin is a 2016 college graduate. He had a student loan debt of $30,000. What is his z-score? So this is just the traditional z-score that we saw at the very beginning of the semester. X minus mu divided by sigma. This is a very straightforward question. We just have one observation. We're going to subtract the mean. We're going to divide by the standard deviation. Okay, and that result is negative 0.7. Now I want to think about what is the mean and standard error for the sampling distribution of the sample mean for a random sample of 36 students. Also, what is the shape of the sampling distribution? All right, so we found out that the mean of sample means is just the population mean. We saw that result previously, and so this would just be the population mean, $37,000, which we were given in the problem. What about the standard error? Well, the standard error of the sampling distribution of the sample mean, it is a function of the sample size. It is the standard deviation of the population divided by the square root of the sample size. So we would have $10,000 divided by the square root of 36. So 10,000 divided by 6. All right, and that is 1666.67. All right, so what about the shape of the sampling distribution of the sample mean? So what we know about the shape is that when we have a sample size of at least 30, the shape of the sampling distribution of the sample mean is approximately normal, regardless of what the population distribution looks like. We were not told anything about the shape of the population itself, so we're going to have to rely on the central limit theorem, which says that once we get to n is at least 30, then we know the distribution of the sample means is bell-shaped, regardless of the shape of the population itself. All right, so I'm going to say here, bell-shaped. And we know that because n is at least 30. The other way we could have gotten the bell shape is if we were told the actual population distribution was bell-shaped, then the distribution of sample means would be bell-shaped regardless of the sample size. All right, now we're asked, what is the probability that a random sample of 36 students has a sample mean less than $30,000? Okay, so what I have to do now is I have to figure out a z-score for $30,000. So let's write it down like this. We're asked to find the probability that a sample mean is less than $30,000. And to do that, I need to find that z-score for $30,000. All right, I'm trying to figure out what goes here. So I'm going to come down here and I'm going to find the z-score. I'm going to say z equals 30,000 minus the mean, which was 37,000, divided by the standard error, 1666.67. Okay, now the common mistake that students are going to make here is they're going to divide by the standard deviation of the population. which was, I believe, $7,000, no, $10,000 here. You don't want to use this now because now we're not finding the probability for an individual. We're finding the probability for an actual sample of size 36. So notice what I did here is I took x bar minus the mean of the sample means divided by the standard deviation of the sample means. Because I'm trying to find a probability about a sample mean, not just about x. Now this simplifies to x bar minus mu, because the mean of the sample means and the mean of the population are the same thing. So that would be okay to just use the mean of the population here. But I need to divide by sigma over the square root of n, right? Remember, these are the same thing. And we already calculated that. We already did that right here. All right, so I don't have to go through all that again. I just need to figure out what this value is now. All right, and so this is negative 4.20. That's what I want to find. Okay, now this one is actually a little bit tricky, because here's the problem. I'm at the point now where I need to look up this value on the table. Let me draw the picture of what's happening here. I've got a standard normal distribution. I've got a z-score way over here at negative 4.20. And I'm being asked to find the area under the curve, this out here in this left tail. Well, there's really nothing under the curve over here because the distribution curve goes into basically nothing beyond this point. So the answer is going to be approximately 0. So I'm just going to say approximately 0. Let's take a look at the z-table. Let's try to look that value up, that negative 4.19. It's not there. Look, it only goes to negative 3.49. Why? Because once we get beyond negative 3.9, there's basically nothing left in the distribution. Now, you could approximate it over here. That does give you these extreme values. And if you put one of those values, that would be okay. Or if you just said approximately 0, that would also be okay. All right, and so that concludes a couple of examples for applying the properties we learned about the sampling distributions.